Good morning, everyone. Welcome to this webinar. It's the 26th ETP4HPC webinar. I'm Pascal. I'm ETP4HPC's communication manager, and my colleague Maike is also here to help run the show. For those of you who are not familiar with ETP4HPC, we are a non-profit association that promotes European research and innovation in HPC. We are a private member of the EuroHPC JU, and our role is to propose research priorities for Europe in the area of HPC. So before we start on today's topic, I would like to share a couple of practical information with you. So this webinar is recorded and you will receive the link tomorrow. This webinar is in listen-only mode, but you can ask questions using the GoToWebinar questions panel. That's it should be on the right of your screen. And in the same panel, there is also a handout section where you can find today's slides. Actually, there is more than the slides. Our speakers today are going to mention several white papers, and they are there in the handout section, so you can download them directly. Let's introduce our speakers. So we are very happy today to have Estela Suarez and Kristel Michielsen, both from the Jülich Supercomputing Center from Jülich. What I want to say that today's webinar is a little bit special because it's a kind of a replay of a live session we organized in March at the EuroHPC Summit. It was an emerging technologies for European HPC session. And it was not recorded at the time, so we decided to share it with as many people as possible. We would organize 2 webinars based on the same content, and with the same presenters. So last week we had the first part. It was about unconventional HPC architectures and about HPC architecture integration, subsystem interposer level. And this week, Estela and Kristel are going to tackle 2 other subjects. So the first one, HPC system architecture aspects, managing heterogeneity. This is one of the presentations that was given at the EuroHPC Summit. And the last one about quantum computing, that's a new one prepared especially for you by Kristel and Estela. So Kristel and Estela, I'm going to hand over to you. I was looking at the webcams, and it's the first time we have an all-female webinar. Rather unusual in the world of HPC, isn't it?
Let's take it as a good thing. So do you see our screen? Oops.
Not yet.
Not yet?
Now looks good. Perfect.
Okay.
Yes.
Very good. Good. So shall we start?
Then we can start.
Very good. So thank you very much for the introduction, Pascal. Now let's go into the first topic, which is heterogeneity, or how to manage heterogeneity in HPC. So we see that in HPC, heterogeneity is growing in our systems. On the hardware side, there are several reasons, but the main reason on the hardware side is that we are needing larger and more energy efficient systems. So it's not efficient anymore. It's not possible to just make a very large monolithic system made only of general purpose processors because they are very power hungry. But heterogeneity is not only on the hardware side, right, Kristel?
No, it's not. Of course, we see it on the hardware side, but we also see that on the application side, more and more codes are combined into complex workflows. And they include simulation, enhanced data analytics, visualization, of course, now popular AI, machine learning, and also quantum computing is coming. Now, all these different codes have their own requirements, and they have to run and also be mapped on these resources, these heterogeneous resources. And this requires, of course, some effort.
Mm-hmm. Yes, so if we look into the architecture side, as I was mentioning before, we have heterogeneity everywhere. So on the processing side, we have CPUs, GPUs, FPGAs, all kinds of accelerators. On the memory side, we are also combining many different memory technologies, DDR, high bandwidth memory, non-volatile memory. And on the network side, also different networks, different protocols are being used. There is even one step further. We are starting to combine paradigms that come from this classical CMOS-based computing with neuromorphic, with quantum computing. So if you want to learn more about all this in detail about the heterogeneity that is growing, we have a white paper on ETP4HPC on this topic. One another aspect is it's not only many different devices put onto the systems, it's also that these traditional barriers we are used to think about, like the processor responsible for computing, the memory for and the storage for storing data, and the network to communicate. So this is a little bit dissolving. We are seeing that computing is the node processors anymore, but also in the network with DPUs, with IPUs. And also there is a lot of research going around processing in memory. For this, there is also a white paper from ETP specifically on the subject. So there are also things like network attached memory are coming up.
But how can one then manage this heterogeneity in HPC? First of all, one starts with the system architecture, our hardware. So there we have to see how can one combine and also connect these various resources, heterogeneous resources that we have, taking also into account the integration of new technologies like, for example, quantum computing. Then for an effective use of the variety of resources, we have to have resource management software that can dynamically orchestrate these resources, also taking into account the malleability of the applications. So then to master the large hardware set that we have and to foster the performance portability, we need tools. And these tools are standardized programming models, also smart compilers, runtime and workflow systems, but of course also the debugging and performance tools. Then important is also the application side. And for the application side, we need models and algorithms which are enabled by these heterogeneous resources. And this is not only a challenge to do this, but of course it opens also new opportunities for novel workflows, novel mathematical formulations, and also new application features that are hybrid in the sense that will combine HPC simulations and concepts of artificial intelligence. So summarizing, we can say that if one wants to manage this heterogeneity in HPC, that one has to address this heterogeneity at a coordinated level, a coordinated effort at all levels. So starting from the hardware, software, but going to applications. One really has to address everything simultaneously.
Mm-hmm. Yes, and one thing to keep in mind is that this heterogeneity exists at different levels of the machine. So several years ago, so around the 2000s, we were used to the very simple view of the computer world in which you had a CPU with just one core, and from generation to generation, the performance was being gained by just increasing the frequency, just getting faster and faster clock in the processor. This stopped with the end of the Dennard scaling, so we could not anymore afford continue increasing the frequency. We had to move into the so-called many-core or multi-core era, where processors needed to increase the amount of cores in order to achieve higher performance. And this became even more complex when we started to include also accelerators. So when it's not only CPU cores, but also, for example, graphic cards or other kinds of accelerators. And one important question in this context is then how to orchestrate these accelerators and these processors into the system. One approach for this is something developed in Europe, which is the modular supercomputing architecture. And the idea there is that we build clusters that we call modules. So modules are just clusters of potentially large size, each one of them with a different node architecture, but inside of this module, one tries to be as homogeneous as possible. So the cluster, the CPU cluster, is made just of a general purpose multi-core CPU. The booster is then made of a system mostly centered on accelerators. In the current generations, these are graphic cards that allow for high scaling and for high energy efficiency. And then when we have specific applications with specific needs, like on data analytics, we can think of different node designs, different system designs, but attaching these modules all with each other. So depending on the application profile, depending on the requirements of the user, they can select which resources to use in this kind of these modules. And interestingly, in this concept, we can also naturally integrate things like neuromorphic and quantum computing.
Yes, so Estela, you already mentioned the modular supercomputing architecture is made in Europe, and actually it started over 10 years ago with a series of deep projects. And in these deep projects, several prototype systems have been deployed, and there was also a full software stack developed for such kind of pilot systems, prototype systems. Now, these deep projects are now continued in 3 C projects, at least the research and development part of it. And these C projects are now funded by the EuroHPC joint undertaking. Now, one of the systems or modular systems that are coming out of all these activities, and that is currently in use in Jülich, is the EuroHPC supercomputing system that we have, consisting of a cluster and a booster, so really a modular supercomputing architecture. Now, it's not limited to Jülich, because in the meantime, also other computer centers started with this modular supercomputing architecture, and we have here as a clear example Michielsen in Luxembourg, and also Leonardo in Italy. Apart from these C projects, there are 2 other pilot projects which are funded by EuroHPC joint undertaking. One is the EuPEX project, in which a European CPU processor will be integrated, and this is especially developed for HPC. And another project is the HPC QS project, in which a quantum simulator, which is a type of quantum computer, will be integrated in an HPC system in Jülich, and also one in CA in France. This is not the end, because the first exascale supercomputer in Europe, Jupiter, which will be hosted in Jülich, will also have a modular supercomputing architecture. And I'm quite sure it will even continue. So, but it's clear that about what I just mentioned with this modular supercomputing architecture, that here we are talking about heterogeneity at a system level. But Estela, before you also have been mentioning that it's not only at the system level that we see this heterogeneity.
That's absolutely true. In fact, we are growing in heterogeneity at the chip level. So in the traditional way, chips were built by a monolithic piece of silicon made just cut out of a wafer. These chips have become larger, or needed to be larger and larger across generations to improve and to get even better performances. And at some point, there is also economic balance on how large can this kind of chip chips become. And there is a trend to go now to the opposite direction and make chips out of individual dies or individual chiplets. So you have many little pieces and you put them together onto an interposer and create your chip in this way. This has some advantages because the yield is better and you can also include more functionality, so you reduce the cost. And there is the possibility, as you see on the picture on the right, to then combine different kinds of chiplets. So not only CPU-based, but also GPU-based, different memory technologies, vector processing units, I/O interfaces, all of these integrated in the form of chiplets. What does it mean? It means you get much more diversity. You have the potential to design your chip for specific markets just by changing the combination of chiplets, for example. And also you get between all those devices shorter connections, so lower latency, better bandwidth, and lower power consumption. Speaking about power consumption and also speaking in general about what is the implication of this heterogeneity at the different levels of the system from node to the full system, one important implication to keep in mind is that it becomes more difficult to understand and to predict performance and energy efficiency. So the system is much more complex. There is a lot of interdependencies between the different hardware components and the different software components. And when you get an application onto the machine, it's hard to say what is then my peak performance for this specific application. Am I close to this or not? And not forget, it's not only performance, also energy efficiency is important in this evaluation. So what we need is a much more qualitative and quantitative evaluation of this HPC system. So we need a large scale, actually exascale system modeling, and end-to-end performance of the performance models of the applications that allows us to correlate so the parameters of the application with the parameters of the system. So what happens when I change, for example, some parameter, some way in which I am operating my system, what is the consequence of the performance of the application, and the other way around? What is the performance of the implication on energy efficiency when my application does something different? They are on this kind of analysis, techniques based on machine learning and AI are quite promising. But in general, the message here is we need a lot of research in this heterogeneous hardware and application model. And I'm speaking here only about the kind of traditional devices, so CPU, CPUs, and things like that. This is even more interesting and actually difficult if we are thinking about more innovative technologies. And you are the best person to speak us about that. What happens with disruptive technologies?
Yes, so as you mentioned, Estela, it's important we have to look for improvement in performance, but we have to take into account that we cannot keep on consuming so much energy as we are doing nowadays. So it's clear there is time for new technologies, as there is always a need for new things. So, and it's clear that here the end of Moore's law is really fueling such disruptive solutions. And we can think about these ASIC-based solutions, but also the more exotic maybe like neuromorphic computing and also quantum computing. And it's clear that we have a huge user base in HPC and that we have to take our users with us. We cannot make an abrupt change in our technologies. Another thing that we also have to take into account, it's clear these are new technologies, new disruptive solutions. So they are far from a productive level. So this also means that we have our applications which are quite well running on our HPC systems, but that we cannot immediately port these huge codes of our user base on these new technologies. So we will have to do this step by step. And it's also clear some of them will also never be running on these new technologies. And maybe then we have to really take into account these new technologies might be special purpose modules if we are talking in terms of our modular supercomputer architecture. So the idea, therefore, is that we have to integrate our traditional HPC technologies with these new technologies. And then we have the advantage that we can still have our well-known applications that are running on the HPC systems And maybe there in the workflow, there is a small part in the computer program that we can give offload to a disruptive technology. And this can then be in principle of any of the kinds that I have been mentioning. And as I mentioned before, the advantage is that also this gives the opportunity to our users to get familiar with these new technologies. And on the other hand, these new technologies have then also time to mature. So that's a nice combination, but it's also clear that for such an integration, of course, we need new hardware and software solutions. So we have to work there on a full integrated hardware and software stack.
Mm-hmm. Yes, so you're absolutely right. Just to give one example of what could be this kind of disruptive technologies. So I speak here about neuromorphic computing. So neuromorphic computing is some kind of device that tries to reproduce in a way how our brain operates, how our brain learns and do some computations. There are different scenarios in which this neuromorphic computing can be combined with HPC. And I present here two scenarios that are also in more detail described on the white paper on unconventional HPC architectures. And one is using the neuromorphic computing at the edge in thinking about of a federated infrastructure where you are from the HPC to the cloud to the edge devices. We can use neuromorphic computing on the edge to do AI inference and training at this level. So avoiding to transfer data back and forth across all these very large federation. But also in the data center itself, in the HPC side, neuromorphic computing can be used as coprocessor accelerators for AI and machine learning training and inference at scale. So for example, inference of HPC AI hybrid workloads, or also training an AI algorithm like a spiky neural network or backpropagation. You have another example, Elena?
I have another example. So another example of such a potential accelerator are the different types of quantum computing technologies. And therefore, the plan is to integrate them in the HPC systems. And this can be done at different levels, and we will discuss this further on, Estela, when we have our presentation on quantum computing. But I can already tell you we have to pay attention for integration on the system level, also on the programming level, and finally, of course, on the application level. And on this, we also have a white paper in ETP, which we learned at the beginning of our presentation, that all viewers can download this. So as it is with HPC, also for quantum computing, application-centric benchmarking is important. We have to test our algorithms, and we have to see that we develop there our software stack and the technology together. So we have also here a co-design approach. Then for this benchmarking, emulation of quantum computers and quantum simulators is essential, and this we do on our HPC systems, but we can come back to this later to a step.
Yes. So to conclude this part of the presentation, this first presentation, so heterogeneity in HPC brings many challenges. This cannot be denied. So it's harder to efficiently serve resources when they are so diverse and to maximize their utilization. It's hard to identify sources of performance loss and optimization opportunities. It's also a question how to maintain performance portability across all these different technologies. And it's also difficult to understand and predict performance. But there's not only challenges, I hope.
No. We also have opportunities. So one of the opportunities is that we can have a much better energy efficiency. And there I would say quantum computing is a very nice example because they use much less power. So then there is, for the user, the ability to select either hardware for each part of his or her application. We have also a wider range of providers and technologies. So this allows us to move away from these monopolistic scenarios which we have more or less nowadays. And another opportunity is the development and the integration of these new disruptive technologies, so that they have, or that we in the end have, an overall better performance and also an overall better energy efficiency. And of course, there is a real impact that we see of the co-design approach.
Very good. So this was the end of our first presentation, yes. And I'm so happy to have you here for this one, because quantum computing is your field. But so let's move now a bit more in detail, and one of the last things we were speaking about on quantum computing. So quantum computing is kind of the big promising thing nowadays. So it promises to solve some of the toughest problems that we have in science and society. So to address optimization problems on supply chain logistics, on traffic optimization, and also on the energy grid management, so important nowadays, but also to be used for machine learning on biological-based problems, such how to use so the human brain functionality, and also vegetation and evolution, which is very important on the context of the climate change. Last but not least, also it has potential for drug design and for materials design. And maybe you can give some example of how it is used on materials design.
Yes, materials design is of course very important, because it's an ingredient of many products, and a potential promising application there is battery design. Now, in battery design, the great computational challenge is that one has to deal with multi-scale modeling. And this is not only in this battery research, we also see this in the understanding of the brain functionality. So this is something in common for these complex problems. So in multi-scale modeling, we learn there from the simulation that happens, or the problems, the complexity that happens in one model level of our model, how this is transported to all these higher levels. So usually we start at a macroscopic level, and then we have to transfer what happens in this microscopic level to the next level, up to the really macroscopic level where we make our observations. And yes, then the issue is that if one wants to develop full battery components, which are based on a comprehensive prediction of the properties of these components, then one needs to integrate all these computational levels. So going from this microscopic level up to this macroscopic level. And one can do this on an HPC system, but in general, this is slow, and often it's also inaccurate. So here again, there is some hope that new computing technologies can be of help, and there is hope that quantum computing can do this. Why? That is, we have in quantum computing a special type of quantum computer, which is called a quantum simulator. And on this quantum simulator, we can, which is a real device, we can simulate the electronic correlations in battery materials. So the hope is, if we can develop a large enough quantum simulator, we can naturally simulate how these electrons correlate in the material.
Okay, very interesting. So no wonder that there are very important goals set on Europe for quantum computing. So in Europe, we have the main goal of establishing a pan-European federated hybrid high-performance computer and quantum computer simulator infrastructure, so to bring together HPC and QCs, with uniform and easy and affordable access for European scientific and industrial users. So the goal is actually to have several and different kinds of technologies, different kinds of quantum computers and quantum computer simulators, so that also to find out which ones are the ones most promising. So to find out which kind of applications work better for them, for which kind of technologies, and to make this publicly available with supports and services. So yes, I think this is yours.
Yes, that is. So we have already several quantum computers installed in some of our HPC centers, and soon there will definitely come more. And as we already mentioned, there are different types of quantum computers. We have two big groups. One group are the analog quantum computers, in which the qubits, so these building blocks, the quantum bits, are controlled simultaneously. Then on the other hand, we also have the digital quantum computers, and there the qubits are controlled individually. So in both classes, we already have installed, or will soon install, some machines. So one analog quantum computer, for example, is a quantum annealer. And in Jülich, we have one installed and operational since 2021. And this is a quantum annealer which is based on the superconducting qubit technology. Then by the end of this year, as well in Jülich as by CA in France, there will be a quantum simulator installed. So the device I have been talking about before for this battery design, and this is a machine that has a different type of qubit technology. So this system is based on neutral atom qubits. And both machines are funded by, as mentioned before, EuroHPC joint undertaking in this project HPC-QS. So it's this machine that will be integrated with the HPC systems. Then I come to this second class of quantum computers, which are the digital quantum computers, also known as the gate-based quantum computers. And there we have well-known examples as the IBM and the Google machines, but we also have such quantum computers which are developed in Europe. And in Europe, a well-known company developing such devices is IQM. And with IQM, their systems are also based on the superconducting qubit technology. But there are many others, like the trapped ion qubits, of which we also have a European company, AQT. I'm not going to mention them all, because the amount of companies and startups is really growing. So we have the trapped ion superconducting qubits, neutral atom qubits, NV centers in diamond photons, and even more. Now, the idea is in Europe to install several of these technologies or devices with different technologies in the various HPC centers, so that the users can get expertise with different machines. That is in their benefit. And it's also in the benefit of the manufacturers, because the users can then contribute to the co-design feedback group, because we have here also a co-design approach as we know it from HPC. So in the end, we will really have this co-evolution between the user with its applications and then the manufacturers with their quantum computing devices.
Yes, so this is very interesting. So many different, so it says how dynamic this research field is, so many different technologies evolving in parallel. But I think it's important, as it was said already before, the integration with HPC. So because for practical quantum computing, you need to combine together the advantage of quantum computing with the performance, with the capabilities of HPC. So the goal is to put them both together and to help to collaborate with each other, find also hybrid applications that can maybe parts of them run on the HPC system and part of them run on the quantum computer.
And it's here where the heterogeneity comes back.
Exactly. So that's also kind of a picture of modular supercomputing. But by the way, there is also a white paper on ETP, but we didn't put on the slides. Anyway, but there is a white paper on that, right, as well?
Yes, there is one on this too. Yes.
Yeah.
So So, and then we come back to this slide where I said that I will give a little bit more detail in the upcoming slides. So this integration of the quantum computer in the HPC system has to be done on different levels. So we have the system level, where we can have a loose and a tight model of the integration, and I will show it in more detail in one of the next slides. Then, of course, on the programming level, as mentioned before, here we have to develop a full hardware-software stack, taking into account this integration component, which is an extra complexity, so to speak, which brings us together. Then we come to the applications, and you mentioned in the beginning, we have 3 big application fields, so to speak. Optimization. There are many problems in optimization, so many industries have all kinds of optimization problems. Then we have quantum chemistry, where quantum simulations have to be performed. And we know that these are hard simulations for HPC systems. It can be done, but the hope is that quantum systems can do this better. And then we have quantum machine learning, which is then also something that could contribute to AI. Applications and benchmarking here is very important, also for the co-design. We have to test algorithms. We have to develop also an application part of the software stack. So we have to see that our users can efficiently, but also easily use this heterogeneous hardware. And then, as I mentioned before, of course, it's very important that we can emulate these different technologies on our HPC systems. Not only these realistic devices, but also the ideal one, because we should not forget, Estela, this is a special, quantum computing is something special. So this is a technology which has as a start a theory, quantum theory. So usually that's not the case for technologies. Then we simply engineer them, and then we try to understand what these things are doing. And one example there is the steam engine. So it was working, but before we understood how it was working, this took us physicists a little bit more time. So if we have these emulators, then they give us also the possibility to design other devices. And of course, we can then analyze and benchmark not only the devices, but also how these algorithms, applications are implemented on the devices. So here a few words extra about the integration first on the system level. So one can think about standalone machines where we have a quantum computer, for example, here, and where we have the HPC system, maybe somewhere in Finland, because there they have nice cooling opportunities. But they can also be co-located, where we bring them closer together. Closer together for the moment being can still be quite some distance, maybe in the same building, maybe in another building, but not too large distance. So that we can already have a deeper integration. We try to go to a deep integration of both technologies. And if I'm speaking about that, then ideal would be, of course, if we could bring the QPU or also on chip. So again, heterogeneity, but then at a different level. So then programming level, of course, it's clear that here we have an entire software stack that goes from controlling these qubits to the user interfaces for the applications. And as I mentioned, this we have to see also as a hybrid software stack, taking into account also our HPC system, and there are various challenges. On the application level, there we have these three groups of applications that I mentioned before. So emulation of these quantum computers and simulators with HPC systems. Why do we do this? To validate the design of the quantum processor so that we can understand why a quantum computer is not doing what it is supposed to do according to quantum theory, and then see, can we do something about it in the lab or the manufacturers? And then, of course, also to investigate the performance of quantum algorithms for applications. There are various emulators available, and in Jülich we also have one developed, which this is one of the older emulators. It's called Jülich Universal Quantum Computer Simulator. It's a state vector emulator, and it has set several world records. Yeah, nice thing is this in collaboration with Riken in Japan, where we could simulate a quantum computer with 48 qubits, and we also had a collaboration with China on this. Then to test the performance of an algorithm, and in the same, I would say, research collaboration, also test the design of a quantum processor, we had a collaboration, or we were one of the collaborators of Google to benchmark their well-known Google quantum processor Sycamore, and with which they reached quantum advantage, we could say, for the first time, although it was for a rather abstract application, which does not really have an application in the real world. But this was a real milestone.
Definitely.
So an application-centric benchmark example. Here I want to address an example from optimization, because there are so many optimization problems around. And therefore, the gate-based quantum computer, or this digital quantum computer, there exists a variational quantum algorithm. And actually, this is already a hybrid algorithm. So there is a quantum part and there is a classical part. So the quantum part, there is a quantum algorithm to calculate an energy expectation value, something for which a quantum computer is supposed to be a good device. And to do this, there is an iterative process. And in this iterative process, we have a parameterized unitary transformation. The word says it's parameterized, so we have some parameters there. And for this, we need an optimization. And this optimization we give to the, still in this case, to a classical computer, a conventional computer, to optimize these parameters of the unitary transformation. Now, to see how this works, we have taken a small example, and it's an abstract example, something from computer science. It's an optimization problem which is called two-satisfiability, and we took a small one with 8 qubits. Why such a small one? Because we did not have big quantum computers to test on. So we have then implemented this quantum approximate optimization algorithm, this hybrid algorithm, on a real device. And the real quantum computer was an IBM quantum computer with 16 qubits. So on the right, you see here the energy distribution in as a function of these two parameters. Now, we do benchmarking. So what we did is we implemented this whole hybrid algorithm also on our conventional machine. So part of our machine was playing the role of the quantum computer. And then on the left, you see the outcome of the simulation. Now, you see, it's difficult to say that the IBM did as good as our ideal quantum computer. Therefore, it's always good to do cross-platform benchmarking. So we went to another technology, and the other technology is quantum annealing. Why? A quantum annealer is actually built to solve optimization problems. So, of course, this machine is much bigger. It was one of the old generations, so this one had more than 2,000 qubits. So we could put several copies on it. And actually, here we studied 5 different problem instances. And we made then a comparison how good the quantum annealer could solve the problem. And you see the success probability in green for the quantum annealer. And then we looked at this quantum approximate optimization algorithm. But to make the comparison more honest, we said, okay, we take the simulation results for the ideal quantum computer. And then we have here the orange bars. So what do we learn from this? We learn from this particular example that quantum annealing is better than this quantum approximate optimization algorithm to solve the problem. But we also see that the quantum annealer for problem instance 4, for example, can also have a hard time. So it's no guarantee that one takes one technology to solve the problem. Maybe there is another one that can do it better. And therefore, we need such a large variety of quantum computers to test.
Mm-hmm. That makes totally sense. And that's also the approach that Europe is taking on that. So you spoke about HPCQS. So there are already 2 sites, CEA and Jülich, that will have this hybrid HPC quantum computing infrastructure. And at the same time, EuroHPC EU has selected 6 further sites where more or less the same approach in the sense of combination of quantum computing and HPC will be tackled, but with different technologies.
Yes.
And as I said before, this whole thing is federated, so users can have access to different technologies and see for which kind of problems, which kind of machines are better suitable. So the goals are, as you see here on the right, so it's developed and provide these HPC quantum computing services for the benefit of all the Europeans, provide uniform, easy and affordable access to those resources, and also very important to train specialists in quantum computing, because this is a very new field and there is not so much in the education, the standard education about that.
No, so that's definitely true. And as you said, this is a plan. Yeah. So what we see there, HPC2, is by the end of the year, the machines will be installed, and then we can really start with the integration. And then these 6 others will follow. These are not only different technologies, they might also have another type of this integration, like coupling. Yeah, of coupling. So I have been talking about this more standalone or this co-located. So there will be different options, because in the end, it's new technology. It's something new that we have to integrate. So we do not yet know what is best. How to best do it. Yes.
We need to look into different directions.
Yes. Yeah. And then the idea is indeed of Europe to fully integrate all these sites into this big European federated hybrid infrastructure. And as Europeans, we can really proudly say that already these activities and even these plans are the first of the kind in the world.
Definitely, yeah.
So then I can imagine that you would have the question, yeah, nice, but when can I access such
Not only me, but the audience mostly.
So, and who can do this? I'm also proud to say that in principle, this timeline in which everything is planned to happen is quite short. So already in 2024, the project members of the HPC2S project will be able to run their first tests and prototype applications on these integrated infrastructures in Jülich and in Paris. And in 2025, this access will be then also given to the stakeholders of the project. And these are other HPC centers, but also researchers from universities or research centers. And the idea is also to have some, let's say, pilot users from industry, which are then, the industrial end users. Of course, they have to come with applications that can be simplified and downsized to run on such a system.
Something like benchmarks size, mini-apps.
Mini-apps, yes. And it's clear that in the stakeholder group, there will be also software developers and service providers. And as you mentioned before, we also have to take care that we give sufficient training and support, not only in quantum computing, but also in this integrated quantum computing and HPC. Then in 2026, we are of the opinion that then the other 6 sites will be accessible for industrial and academic end users. And then we have the hope, and there are some also some indications that by 2027, there will be a project funding or maybe even already installed that we can talk about this federated HPC quantum computing and simulator infrastructure, which is then accessible for European users.
Excellent.
So if you are interested in first access, then of course you can follow us, and us means EuroHPC joint undertaking, and then first of all HPC QS on our websites, on Twitter, and also LinkedIn.
Yes, I will follow you, and I hope also that our audience will follow you as well.
Yes.
Thank you very much, Kristel. I learned a lot about quantum computing, and thank you all for listening. We are open for questions.
Thank you to Estela.
Thank you, Kristel and Estela. This was really interesting, and we have a number of questions, so I will share my screen if I can here. Yeah, okay. So if you have questions, you can ask them in the questions panel. And I copy all questions in the chat so everybody can see them. So we have a number of questions already. Kristel and Estela, you can see them either in the questions panel or in the chat. And let's take the first one. So the first one was received quite early in the presentations. It was from Anastasia Andreevska. What do you think about quantum neuromorphic?
I must say, I'm not an expert in neuromorphic computing. If there would be another hybridization between quantum and neuromorphic, this would, of course, be very interesting. Of course, if we would integrate neuromorphic and quantum processor into such a modular supercomputer architecture, so if we would have this heterogeneity, then of course I can imagine that we have also applications that could use also these 2 technologies, or even in combination with HPC. I would not exclude this.
Okay, thank you, Kristel. So next question is from Joachim Erdberg. By the way, hello, Joachim. Nice to have you. So many applications currently in use are not ready for the future you describe. What specific actions do you recommend to accelerate software modernization?
Well, there are different, it depends a bit on the application, on let's say on the status of the application that you have right now. So the first thing before you go, or before considering even quantum computing or other things, is about the general heterogeneity, on different kinds of devices and so on. So for this, there are high-level programming models that might help a little bit. So things like Cocos, Raja, Srikul, I mean, all these names try to help a little bit to abstract from the hardware, from the specific hardware device to from the application. So the application focuses on just the physics or whatever science they are doing, and don't need to take care so much about the hardware. That's one approach. There is also, well, in Europe and in many of other centers, there is a lot of training opportunities for improving the applications themselves in terms of scaling, in terms of portability, and so on. But in general, I fully agree with you. There is a huge effort that needs to be done by the different user communities, and there are many support actions and support teams on the different computer centers that try to help on doing that. But the heavy lifting remains on the computational scientists, on the application developers. There is the hope that the centers of excellence, for example, from European Commission and EuroHPC help on doing that. But there is no way around going back to the cause, looking into, okay, how are they prepared? How are they well suited for different kinds of devices? What needs to be changed?
Yes, so to speed up these things, I think we also have to see that the computer scientists, or that we have computer scientists who are willing to invest time into this type of, let's say, trying out and making them familiar with the new technologies. And yeah, this means investing time and not having then, yeah, for a while, the opportunity to run production runs and write scientific papers on the scientific outcome, but more on the trying out of the new technologies.
And one thing that is a lot of discussion in the community is about how to recognize this effort. So what's about the research software engineering effort that is being done by these people and needs to be done by these people? How do we recognize this? Because that's not a traditional academic career. So you don't gain high-profile papers on your research field on doing that. There's a lot of work that needs to be done by the community in general to find a way to acknowledge this work, I think.
Yes.
Thank you.
But just to be said, just to conclude this, to be said, unfortunately, there is no way around it. So we don't see a future in which this heterogeneity will change. So we have to find the means to adapt applications to this. Sorry, Pascal.
Okay, thank you. Thank you. So next we have a question from Daniele Gregory. Hello, Daniele. The JUQCS is available, open source, and it works on every x86 cluster. That's a question.
It's available on our HPC system. It's not open source, and it actually works on a laptop, and it also works on the biggest parallel supercomputers, either CPU or GPU based.
Okay, thank you. So next we have a question from Manolis Maratsakis. Hello, Manolis. Thank you for this insightful presentation. This is for you, Kristel and Estela. Can you elaborate on loose versus tight models of integration at the system level? In particular, which type of models would be easier to integrate with existing resource management in HPC systems?
This is mostly about you, so the integration of quantum computer onto the system.
Yes. Yeah, so what is easy, of course, to integrate is if we access, so to speak, both systems on a cloud basis. So if we have cloud access to the quantum computer, if we have cloud access, or whoever one wants to name it, to the HPC system, and then run your hybrid algorithm. Of course, then we can do this, but then we don't take any latency into account. If we have, and then we can still play with the schedulers on the HPC system when we address the HPC resources or when we will address the quantum computing resources. When we are talking about a modular supercomputer architecture, there we also integrate different types of resources. If we do there a deep integration, we do this on a software level. If we are talking about the more tight model of integration, then we are here also talking about taking this quantum module as on a similar level as a GPU model in a modular supercomputing architecture and do the integration and make use of both types of resources. So this means that in this more tight integration model, we are now expanding this modular supercomputing architecture software that has been developed for this.
I have nothing to add on my side.
I have nothing to add. Okay. So I don't have any more questions, and it's time anyway. I just have a message of thanks, so I'm going to read it. Thank you very much for the interesting presentation. Great experts and great team. Congratulations. This one was from Anne Bernard Bedouet. So
thank you, Anne.
Thank you very much.
And thank you everyone for listening and being there and posting questions. I hope it was good for everyone.
Yeah, thank you. So thank you very much, Estela. Thank you, Kristel. This was our last webinar before the summer break. So thank you to our audience for being here today, because this was one of our most successful webinars, again, in terms of number of audience. So congratulations, everyone. And yeah, I wanted to just to give you a short information. Next webinar will be in September on the 15th, and it will be about LUMI, about the LUMI EuroHPC system. We'll have Pekka Maninen talking about it and presenting not so much the system, but what they've done with it, you know, use cases. Thank you again, and have a nice summer, and talk to you in September. Bye-bye.
Bye-bye. Thank you, Pascal.
Thank you.